Welcome to the playlist on our fourth topic, which is energy. And this is a very, very big topic in AP Physics 1. It was a big topic in Regents last year, but in AP 1, there seems to be a large emphasis on forces, energy, and momentum, even more so than there was last year. So, that being said, we're actually going to attack this topic, energy, kind of backwards from what we did last year. You should remember a lot of the basics of this. There's not a ton, I guess, new that we're going to learn strictly about energy, but you are going to get some much more difficult problems this time around. So, first of all, you might remember last year we actually had some trouble defining what energy is. It's a very vague term. The best that I've come up with, or the best that I've seen in my college physics textbook, is a description that goes sort of like this. Energy is a quantity that allows an object or system, remember a system is simply a collection of objects, to either move or have the potential or ability to move if circumstances change. And that is very vague, but I think you'll see what we mean by that as we go. Let's just get right into it. The units of energy are joules, Joules, symbolized by a capital J. And a joule is equivalent to a Newton times a meter. We'll see an equation probably in the next video that features that. And that means that they're also equal to a kilogram times a meter squared over a second squared. And last but not least, before we get into the real important lessons that we have to learn, we do need to talk about the fact that this is a scalar quantity. Direction does not matter for energy. Probably the most important thing about energy, and possibly one of the most important facts in all of science, really, is something called the law of conservation of energy. This states that energy can be transferred between, it doesn't even look like 2 hours, there we go, between objects or systems, or between different types of energy, so you can move object or energy from one object to the next, you can move energy from one type to another, but you can never energy can never be either created or destroyed. And that is a universal law that we have seen. Now, you might be thinking, well, there's lots of exceptions to that, right? Like, what do you call like a power plant that's generating energy? What it's doing is taking energy in one form and converting it to another form that we can use more easily. Energy cannot be created or destroyed, okay? The universe has a set finite amount of energy in it, and it has had the same set finite amount of energy since its creation, and it will have the same exact set finite amount of energy until the universe ends. All that happens in the meantime is that energy gets moved around into different objects, different systems, or converted from one type of energy to the next. Now, on a smaller level, we can actually look at systems, and we can say that in what is called a closed system, events, or just things happen. So events happen that transfer energy, but the total energy doesn't change. In other words, if you have what's called a closed system, the definition of that is a system in which the total energy remains the same. If you don't have that, you have what's called an open system. But one of the neat things about systems is you can always expand the definition of system to make anything a closed system. Okay? So for instance, if you have a ball that is falling and gaining, let's say, kinetic energy, which we'll talk about in a second, you might say, oh, well, that ball is gaining energy. That seems like an open system if we just count the ball. Well, that's true. You could make it a closed system by saying, okay, well, what's causing the ball to fall? The gravitational pull of the Earth. What if I now count the ball and Earth system? Okay, the system consisting of both the Earth and the ball. In that case, you have a closed system. The energy is maintained between the system consisting of the ball and Earth. It starts as gravitational potential energy and ends up as kinetic energy. You might say, well, okay, what about air resistance? Well, if we then account for the system of the ball, the Earth, and the air, we now have a closed system again. If we just account for the ball and the Earth, you might say some energy is lost or destroyed, but if we account for the air, causing the air resistance, you find that that's not the case. So, defining a system in this class is absolutely crucial. Before you start an energy problem and you're trying to think of how to go about solving it, you should figure out, okay, well, what is my system? What set of objects are passing energy between them? There's an equation that symbolizes the law of conservation of energy, and it's a kind of silly looking one. It is ET equals ET, which you might be saying, well, duh, something has to be equal to itself. What it really means is the left-hand side is like the initial side, the right-hand side is like the final side, okay? So that's what ET equals ET really means. In a closed system, the total energy doesn't change. Total energy before an event is equal to the total energy after an event. And what we use this for, this is used to calculate how much energy ends up in different objects or forms. So this is the basis of our kind of bookkeeping. Okay, this is the basis of how we're going to track how the energy transfers from place to place as time goes on, or as before an event and after an event. Okay, and again, we're going to get lots of practice with this on the homework and in class on how to actually deal with problems like this. Let's talk about types of energy. Okay, there's four main types, same four types that you talked about last year, that we'll focus on in this class. And the first one, very, very basic, you probably remember this very well, it is called kinetic energy. And kinetic energy is simply the energy that has to do with an object moving. The energy of motion. Last year for a symbol for kinetic energy used Ke. This year we're just going to use a capital K. And you probably remember the equation, it's a very easy one to remember, is 1/2 mv squared. K equals 1/2 mv squared. And as you can see from this, the kinetic energy should never be negative, because even if you had, let's say, a negative velocity, something moving backwards, when you square it, it's going to become positive. Mass has to be positive, therefore kinetic energy has to be positive. Can never be negative. It can be zero if an object isn't moving, but the kinetic energy can never be negative. Let's move on to another one. We also have gravitational potential energy. Gravitational potential energy. And it is important to say gravitational potential energy because, as you know, there are two types of potential energy that we will talk about. Gravitational potential energy is energy that is associated with a force of gravity between two objects. It's important to remember that if we're talking about gravitational potential energy does not exist unless you have a system with two objects in it. So I'm just going to make a little note about that. System must have at least two objects. So, energy associated with a force of gravity between two objects. Every two objects in the universe have a force of gravity between them. And later on, we're going to find the equation for calculating that force. Well, not only we know from last year how to calculate the force of gravity between them. We could also figure, you'll see an equation towards the end of the year of how to figure out the gravitational potential energy stored because of the force between any two objects. You guys are used to the very basic equation for gravitational potential energy, which we can use in 99% of the cases this year. There is one time where we might want to use something a little bit different, but we'll get to that when we get there. Okay, so you guys saw it. The equation last year for this is UG. Oh, by the way, the symbol is no longer PE with a little g. It is U, U sub g. U is the symbol that we use for potential energy. It's kind of a random one, but it's capital U. It's something you're going to have to go with. Okay, so UG equals mgh, where m is the mass, g is acceleration due to gravity, meaning this is the equation that we use for objects that are like on a large planet, and there's an acceleration due to gravity there, and h is what's known as the height. And that's a little misleading, because this is actually, and we're going to spend a whole video talking about this h here is arbitrary. When we say height, we don't define height again over what. That's up to you to do. You can pick any height to be what is called your h equals 0 height, 0 meters height, as long as you stick with it. So in other words, once you pick a height, you have to stick with that for the rest of the problem. Okay, you can't say that you have one object on the ground and that's h equals 0, another object on the table and that's also at h equals 0. Okay, once you pick an h equals 0 line, you have to stick with that for the entire problem. Okay, so there's gravitational potential energy. That's also fairly simple to deal with. We're also going to talk, let's see, what comes next? Elastic potential energy. It's another potential energy, and this is the energy that deals with compressing energy of either compressing or stretching an object. I guess if you want to replace stretching and compressing, you could say the deformation of an object changing its shape. Okay, the stretching or compressing of an object. Okay, let's see here. Oh, before I forget, all three of these types, they are generally referred to as different types of mechanical energy. It's very easy to change one form of mechanical energy into another. Okay, it's very, very simple to do. It's very easy. Energy can change rapidly back and forth between kinetic energy, gravitational potential energy, and elastic potential energy, and we'll actually see some problems like that as we study this energy unit. You'll probably remember that the equation, well, the symbol is going to be new. Remember, U is our potential energy symbol, and we're going to put an S there for spring. Okay, you could also call it spring potential energy technically, but mu S is the equation, or is the symbol, and the equation is equals 1/2 K, the spring constant, times X squared, with X being the amount of stretching or compressing, not the length, the amount that the object has either stretched or compressed from its usual unstretched or uncompressed length. Okay. Okay, so got a bunch of notes for this one. At the object's unstretched or uncompressed length, there is no, if at the normal length of the object, x would be 0, so us must be 0 joules. It is only added during stretching or compression. And just as a couple other notes, let's see here, what do I want to talk about first? Just like the gravitational potential energy, you needed two objects to have for a system to have gravitational potential energy. That's the same thing with elastic potential energy. The system must be at least two objects. And that's because there has to be an object being deformed, and you also have to have some object that is exerting the force causing the deformation. Okay, so it has to be at least two objects. And one other note with this, you have to be very careful. There's a difference between an object that is unstretched or uncompressed and an object in equilibrium. There's a big difference between those two. An object that's in equilibrium is not necessarily unstretched or uncompressed. Think about a mass hanging from a slinky. That mass has changed the length of the slinky, but it has not necessarily, but if it's changed the length, if it's just hanging there, it could be in equilibrium. So saying something's equilibrium length is not necessarily the same thing as saying it's unstretched length, and that's a key difference between the two terms that you have to be aware of. Let's see here. Okay, so we know that we know that K is the spring force. Remember, or not the spring force, excuse me, the spring constant. Spring constant is how hard it is to stretch or compress something. A high K means it's harder to stretch. A lower K means it's much easier to stretch because that's given in newtons per meter. Something that has a spring constant of 100 newtons per meter is much easier to stretch. It would take 100 newtons to stretch it 1 meter than something that has a spring constant of 1,000 newtons per meter. It takes 1,000 newtons to get that object to stretch 1 meter. And as always, recall that this equation is different from the spring force equation. Spring force is Fs equals Kx. This is Us, the elastic potential energy, equals 1/2 Kx squared. The last type of energy that we're going to focus on is thermal energy, or last year you called it internal energy or thermal energy. So thermal energy. Thermal energy is energy, and I'm going to put in quotes, lost due to friction. This is not a type of mechanical energy because once you convert energy to thermal energy, you really can't convert it back out, at least in ways that we're going to talk about. The symbol for thermal energy is Q. And we need to talk about it because in a non-ideal world, friction takes energy away from the different types of mechanical energy. It reduces, over time, kinetic, gravitational potential energy and elastic potential energy. Where does it go? It doesn't just disappear. It becomes what we call thermal energy. So, what happens is that objects that encounter friction, well, what do? They very obviously slow down. Ultimately, they slow down. And that's kind of obvious because what type of energy decreases when they slow down? The kinetic energy. Okay, so they lose kinetic energy. This doesn't mean that the energy is destroyed. Energy isn't destroyed. But what happens instead, it is transferred from the kinetic energy of the object to other objects or forms. What's really happening is that friction causes, instead of having all the atoms move in the same direction, friction causes them to start to vibrate in different ways. And that vibrate in different ways, it's kind of like saying you're taking the kinetic energy that these molecules and atoms initially had, and now you're kind of redirecting that kinetic energy a little bit so that it's not all in the same sort of motion. Okay? So what you're really doing, what you're increasing when you increase thermal energy, is you're really increasing the kinetic energy of individual atoms as opposed to the kinetic energy of the object itself. And when we increase the kinetic energy of the individual atoms, what that does is it makes them, well, the sensation we would refer to this as is it makes it hot. How do you warm up your hands? You rub them together like this. It makes it hot. What you're doing is you're increasing the kinetic energy of the individual atoms in your hands. One of the unfortunate things about thermal energy, and we're going to end it right after this, is that there's no equation for it. There's a symbol, Q, but there's no one set way to determine what the internal energy of an object or system is. There's no equation, and it must be calculated based on other types of energy. And so in that sense, it's a lot like, let's say, tension or a normal force, in that there's not an equation for it, but you can still determine the magnitude based on drawing a free body diagram and figuring out what all the magnitudes of all the other types of energy are. What this really goes to show is that there's not an equation for Q that works every time, but you can figure it out after using the law of conservation of energy and determining the other types of energy and how they change. When we come back, we'll talk about a few more topics like work and power.